Hi everyone, my name is Yuan Chen. I am a PhD student at HCI Lab of the University of Waterloo. Today, I'm going to present our work, Global Sense Filtering, Exploration, and Pointing in Occluded Virtual Space. This work was done when I was an intern at Huawei Technologies with my collaborators Junwei Sun, Qiang Xu, Wei Li from Huawei, Brian Irony from University of Manitoba, and my advisor Edward Lang. Virtual reality has presented end users with rich 3D environments. An ongoing challenge within VR is the acquisition of targets to support subsequent manipulation. As a result, 3D selection in VR remains an active research area. Most VR systems use some variant of recasting for 3D pointing, which enables users to select using a virtual ray. Among the many concerns with 3D target acquisition, targeting occluded targets is a significant challenge with recasting. There are two types of occlusion, partial occlusion or full occlusion. Each type of occlusion has its own issues. While a partially occluded target can be seen, it is hard to point at it quickly and accurately because of distracting neighbor targets. As for fully occluded scenarios, since targets are completely hidden, it is then hard to locate these targets. While the majority of recasting techniques are used for selecting visible targets, existing techniques that are used to manage occlusion can be separated into two categories: transparency or cutouts and view manipulation. Transparency or cutouts allow users to look through occluding targets. For example, tilt casting uses a virtual plane as a filtering surface, and objects above the plane are invisible, allowing objects that are on and below the plane to be visible. The large-scale cut plane is a cutout technique, which uses a plane to split the entire scene, making one side of the plane translucent and reveals targets on the other side. However, many of these techniques are tuned to select occluded targets at a lower location or provide limited support for visual search during selection tasks. On the other side, view manipulation allows a user to select partially occluded targets or that rearrange targets spatially to handle occlusion. For example, with SCORED, users first specify a spherical volume containing all targets of interest, and then users refine the initial selection progressively by selecting the subset of objects from a 4-item menu until the target is finally selected. Most recently, Yu and his collaborators proposed various recasting techniques to select fully occluded targets, such as flower cone, grid wall, and also grid. All of these view manipulation techniques are designed based on the assumption that target locations is known and at least partially visible to users, or that their location context can be disrupted without cost. However, in many scenarios, we cannot make any of these assumptions. Therefore, we have identified two design requirements absent from existing recasting techniques. The first is the lack of ability to handle both partial occlusion and full occlusion in virtual environments, and the second is the need to explore the environment and dynamically control the interaction space to overcome visual occlusion. Motivated by these design requirements, we propose solar casting, a 3D pointing technique designed to support fast and low error target selection across different levels of occlusion. To achieve dynamic global filtering and local pointing with 1 degree of control, we use a semi-transparent sphere, which we call solar, centered and anchored at the user's head. Solar status depends on touch events provided by the entire touchscreen of the connected device. When solar is triggered, a ray and a cursor are defined in relation to solar's volume. When a ray does not intersect with any object, the ray extends to the inner surface of solar. However, if the extension of the ray beyond solar's surface intersects with an object outside of the sphere, the ray snaps to the intersecting object. We can manipulate solar in two ways, either by rotating it around its center or by scaling it along its radius. By integrating these motions with the view manipulation and transparency, we propose three modes to handle occlusion using solar. The first mode is rotate. Rotate is a progressive refinement technique. It rearranges objects in the environment to minimize occlusion. With rotate mode, users can rotate objects that intersect with solar surface around its center. To perform this interaction, users need to move their fingers horizontally on the touchscreen of the connected device. Hide and semi-transparent modes adopt a virtual X-ray metaphor, which permits users to see through objects between the user and the surface of the sphere, thus making the occluded objects visible. Hide is used to hide occluders, while semi-T turns occluders semi-transparent. To change the radius of solar and apply these two modes, the vertical movement of a finger on the touchscreen maps the radius of the solar. When a finger moves up and down on the touchscreen, the radius increases and decreases correspondingly. In addition, all modes will only be applied to targets within solar and within user's field of view. We also use two-pointing facilitation techniques, bubble mechanism, and wave filtering. Solar casting's bubble mechanism is implemented by selecting the nearest target that is either intersecting with the surface of solar or outside of the solar. For wave filtering, we use the 1 euro filter as it offers a good trade-off between precision and latency. We conducted informal pilot study on our three occlusion modes and their combinations using solar casting to understand the impact of each mode on occlusion and decide which mode will be used in the formal studies. The results showed that rotate was slower than all other modes. This was because participants performed two steps to remove occlusion. They first move vertically on the touchscreen to scale solar, such that it intersected with occluders. Then they move horizontally to rotate occluders away. And when in a combination modes, when participants intended to use hide or semi-transparent, rotate was triggered by accident as they carelessly swiped horizontally. On the other hand, hide and semi-T had very similar performance, but hide had a trend to lower error rate than all other modes. However, for hide, as context is removed, participants have more difficulty searching for targets. Therefore, in our following studies, we choose semi-T as the filtering mode. To evaluate solar casting, we conducted two studies. In the first study, we evaluated the performance of solar casting with the help of visual guidance in an occluded environment. But in the second study, we evaluate its performance without the help of visual guidance. In the first experiment, we use a repeating measure within subject design. We had three independent variables, which were technique, occlusion, and block. And we recruited 12 participants in total, with one female and one experienced VR user. The whole experiment lasted for 60 minutes. We first looked at the results of selection time. We found a significant effect of technique, where depth casting took significantly longer than other techniques. We found a significant effect of occlusion. It took participants significantly longer selecting targets in high occlusion environments. We also found a significant interaction effect between occlusion and technique on selection time. In long and low occlusion environments, solar casting was significantly faster than depth casting, but in high occlusion environments, they have very similar performance. When we look at the error rate, we found a significant effect of technique, where depth rate had significantly higher error rates than other techniques. We found a significant effect of occlusion, where participants made significantly more errorless selection in the high occlusion environments. We also found a significant interaction effect between technique and occlusion, where expand kept relatively low error rate across all occlusion levels, while other technique error rate increased in high occlusion. Now, when we last looked at the subjective measure, we found a significant effect of technique on all attributes except for hand fatigue. Participants found solar casting significantly easier and faster to use, and had better accuracy, hand, and wrist control than expand. They also reported that solar spheres should reset after each successful section, and expand did not work well with high occlusion because they had to try with every cluster. They also reported that depth casting required precise control of the wrist, and it was hard to move the cursor in depth ray because it does not allow filter along objects along the ray. So the main takeaways from study 1. Occlusion had a significant impact on section time and error rate. All four techniques performed more slowly in high occlusion environments. Although users were informed of the target location by the target indicator, it still took longer for them to reveal the occluded target for subsequent section. We also found that slow casting was at least as fast and accurate as the other three techniques with the presence of the visual guidance. Now, in the second study, different from the formal study, the visual cue was removed and a new occlusion design was introduced. In our pilots, we found that expand was extremely time-consuming and demanding significant effort in the full occlusion environment. And without visual cue, participants felt dizzy very quickly, rotating their head and turning around to search for targets. Therefore, expand was removed from the study 2 and targets were all presented in front of the users. In total, we recruited 12 participants. 4 females and 2 were experienced VR users. The whole experiment lasted for 90 minutes. We first looked at the selection time. We found a significant effect of technique. Depth casting took significantly longer than all other techniques. We found a significant effect of occlusion. Participants still spend significantly longer time in full occlusion environment. And we found a significant interaction effect between technique and occlusion. In both long and partial occluded environments, depth casting was significantly slower than solar casting and depth ray, while in the full occlusion environment, there was no significant difference, although depth ray was relatively slower than depth casting and solar casting. Now we move to the error rate. We found a significant effect of technique, where solar casting was significantly more accurate than depth casting and depth ray. We found a significant effect of occlusion. Obviously, error rate increased while the occlusion level increased. We found a significant interaction effect between technique and occlusion. While depth casting and depth ray made significantly more error selections in the full occlusion environment than in the partial occlusion environment, solar casting still achieved high accuracy in both environments. Last, we look at a subjective measure. We found a significant effect of technique on wrist control and fatigue. Depth casting demanded significantly more wrist control and caused significantly more wrist fatigue than solar casting. We found out solar casting had relatively high scores across all attributes. Last, given the local transparency function of depth ray, some participants reported that it was difficult to use and see where the goal target was in the full occlusion environment. This was because targets outside the transparency volume and in front of the goal target might block the view. To handle this issue, some participants believed that a global filtering mechanism along the ray would be much welcome in depth ray instead of on the cursor. So the main takeaways from study 2, we found that across all occlusion levels, solar casting outperformed depth casting in terms of speed and outperformed both depth casting and depth ray in terms of error rate. We also found out solar casting significant accuracy advantage for the full occlusion condition. Of course, we have other things to discuss. The first is about occlusion layouts. Our occlusion layouts were initially inspired by Vaneka's work and serve to create occluding distractors around targets. Occlusion VR could happen with or without visual guidance and within and outside the field of view. Therefore, our designs in both studies were essentially a generalized version of Wu's work. This balance between preserving aspects of prior study design while seeking more representative tasks is very challenging and does represent a potential limitation. We also noted that solar casting design supports very high accuracy, particularly for fully occluded environments, and its speed is at least as good as competing techniques regardless of occlusion levels. However, solar casting required repeated scaling actions, that is clutching, to increase the volume of solar and filter occlusion. We think it is a good idea to explore clutching mitigation strategies, including tuned city gain functions for controlling solar radius, which may reduce clutching and further speed performance. Last, looking specifically at depth rate and slow casting, we discovered that compared with local filtering, global filtering greatly increased accuracy but not speed of selection. During the search point process, participants' attention was limited regardless of the filtering range, while this range controlled by the presence of occluders. Meanwhile, comparing results in both studies, we observed that visual guidance not only greatly increased the accuracy but also speed of the selection. This is understandable as visual guidance is a strong factor to improve participant attention. Therefore, future also includes investigating approaches to improve users' attention with solar casting. To conclude, in our work, we present sourcasting, a dynamic pointing technique for global filtering and selection in occluded virtual environments. Thanks for listening.